Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and as you can see, I'm still on vacation. Got a couple more days left, and this is part two of my sub-series on applications of first-year calculus. And in the last video, I did a video on Galileo's law of falling bodies. This is a continuation of that video. There's actually two more forms of Galileo's law I want to go over, but we won't need calculus to derive them. We just need some algebra. So anyway, let's begin. So here, in the last video, I went over the first two of these laws. So we would derive formulas for the height of a falling object versus time, as well as the velocity, versus time, and we're assuming the object is moving just up and down. So either we drop it from a height, or we throw it up, or we throw it down. It's just moving in the vertical direction. And we saw last time that the equation we get, I think 2 is a little bit simpler. The equation we get for the velocity of the object, usually easier to think of it as a ball. The velocity of the ball as a function of time is given by v of t equals v0 minus gt. And remember, we're using positive velocity to mean upward and negative velocity to mean downward. And then similarly for the height, we got equation in the form z of t equals z0 plus v0t minus 1 half gt squared. Here these constants, v0 is just the initial velocity of the ball, and z0 is the initial height of the ball. So those are the equations we derived last time. But there's a couple other equations I want to derive. They're actually very simple to derive from the first two. So the third equation is velocity versus height. And this is very useful. You might want to know how fast an object is falling as a function of how high it is. I mean, if you drop it from a tower, you might want to know how fast it's going to be falling by the time it reaches the bottom of the tower, something like that. Or if you're throwing it up, how high, you know, what will be its speed at a given height. So it turns out the equation you get for that involves the square of the velocities. You get v squared equals v naught squared minus 2g times z minus z naught. And the velocity could either be positive or negative. It can either be going up or going down. This equation doesn't tell us that, but usually from the context we know. And then the final equation, time versus height, this is another very useful equation. You might want to know, at what time the ball will arrive at a given height. Well, this equation tells you that. And this one's probably the most complicated equation. Involves a square root, but the equation says t equals, what is it? V naught plus or minus square root of v naught squared minus 2g times z minus z naught all over g. And how do we derive these equations? Well, they're actually pretty simple to derive. Let's do the first one. Let's do 3. So to get 3, let's just look at the right side first. And we can simplify the right side a little bit. We can plug in the equation for z of t, because what is that? Z minus z naught? Yeah. Um, yeah. Well, we can just yeah, we know z minus z naught is v. Yeah, from equation 1, we know z minus z naught is v naught t minus 1 half gt squared. So we just plug that in, and when you do that, it turns out you get a perfect square when you simplify everything. You just get the square of v naught minus gt. But we know what v naught minus gt is. It's just the velocity of the ball at time t. So that proves equation 3. We get the left side when we're done. And then you can get equation 4. I don't do it here, but equation 4 follows easily from equation 1. Because you'll notice that equation 1 is really just a quadratic equation in t. And you can bring z naught to the left side. I mean, you can bring everything to one side. You get 1 half gt squared minus v naught t plus z minus z naught equals 0. And when you use the quadratic formula to solve for t, you get the equation 4. So that's how you do that. Anyway, that's how you get those two equations. You don't have to do any calculus. We've already done all the calculus we need. mainly to get equations 1 and 2, and then 3 and 4 just follow from algebra. So anyway, and now I just want to go over some examples. So this is sort of like the example I was doing last time. Imagine we're dropping a ball off the top of the Eiffel Tower, and like I said, you wouldn't want to do this in real life because it's going to end up going down very, very fast. So we're assuming the Eiffel Tower has a height of 300 meters. It's very close to this. I don't know the exact figure, but it's roughly 300 meters. So we just plug in the formula, equation 3, v squared equals v naught squared minus 2g times z minus z naught. In this case, v naught is 0 because we're dropping it. We gave it 0 initial velocity. And our initial height here is, or our final height is 0 because it falls on the ground. So z is going to be 0, but z naught is 300 meters. So when we plug in these numbers, you get v squared equals 5,880 meters squared per second squared. We still have to take the square root, and it's ambiguous because of the signs, plus or minus 77 meters per second, but we know that the ball is going to be going downward when it hits the ground, so its velocity is minus 77 meters per second. That's very, very fast, by the way. I think that's something like 150 miles an hour. And it'll probably be going a little bit slower than that because, it's probably going to reach terminal velocity or get close to terminal velocity. But you still wouldn't want to do this because that's very, very fast. Um, anyway, let's look at a couple more examples. These are similar to the first one. The only difference here is now in example 2, we're throwing the ball down. We're not just dropping it. We're throwing it down at 50 meters per second. So imagine you had a really good baseball player throwing the ball down as fast as he can. 50 meters per second. That's pretty damn fast. That's about as fast as a baseball player, a pitcher can throw a ball. So now we just do the same thing, except this time our V naught is minus 50, so we plug that in, and when we do that, the answer we get this time is what do we get? 92 plus or minus 92 meters per second. Again, we know that we have to take the minus sign because it's going down. So this is going to make it go a little bit faster, 92 meters per second, because we gave it some initial velocity. And suppose we do the same thing, except instead of throwing the ball down, we throw it up with the same speed. Well, it turns out for this example, you get the same answer when you plug in the numbers. It kind of makes sense because we're squaring the speed. We're just starting with v naught squared, so that doesn't care whether it's up or down. You're going to get the same speed, the same velocity when the ball hits the ground if you throw it 50 meters per second up in the air or 50 meters per second down. And the reason for this is basically conservation of energy. I don't want to go into this because that'll take us farther afield into physics. But it turns out that the final velocity of a object hitting the ground only depends on the difference in potential energy if you start with the same kinetic energy. That's why you get the same answers for part 2 and part 3. 92 meters per second, very fast. Let's do a few more examples. So those are examples involving calculating the final speed of the ball. What if you want to know how long it takes? So again, let's do the same examples, except this time let's figure out the amount of time it takes. So suppose we want to know how long it takes if you drop for a ball to fall to the bottom to the ground from the top of the Eiffel Tower if you just drop it from the top. Well, you just plug in equation 4, the ugly one, and in this case, V naught is 0, so you just get, you just plug in the numbers here. I simplified it a little bit on the third line. You end up getting the square root of, whenever you do this, you always get the square root of 2h over g. So in this case, you're going to get the square root of 600 meters divided by 9.8 meters per second squared, which works out to be about 7.8 seconds. So it takes about 8 seconds. It would take about 8 seconds for a ball to hit the ground from the top of the Eiffel Tower. Now, what if you throw it down and throw it up? So those are the last two examples I'm going to do. Here, the formula is a little more complicated, but you just plug in the numbers, and you have this ambiguity about the sign in front of the square root. But you can just kind of use common sense here. I mean, actually, it turns out for both of these examples, you would get a negative value of t if you plugged in the minus sign in front of the square root. So we have to use the plus sign. And for the first example where we're throwing the ball downward, we find that it hits the ball in just 2.8 seconds. So that's a lot faster. If you threw it down, you're giving it some initial speed, so naturally it's going to hit the ground a lot faster than it would otherwise. And in this case, it hits it 5 seconds earlier. In the other example, where we're throwing the ball up in the air instead of down the air, turns out it takes 13 seconds to hit the ground. It takes 5 seconds longer. So, kind of makes sense. I mean, if you think about the arc of the ball, if you throw it up in the air, what's kind of interesting is that it spends the first 10 seconds going up. It spends the first 5 seconds going up to its maximum height, which we aren't calculating here. But then it spends another 5 seconds going back down to where you threw it from. So after 10 seconds, the ball's going to end up where it started at the top of the Eiffel Tower. And now the example is just like the first example. It's going downward at 50 meters per second, so it's going to take another 2.8 seconds to hit the ground, and it hits the ground after 13 seconds total. So that's how that works. Anyway, that concludes my video, my follow-up on Galileo's law of falling bodies. Thank you for watching. Long live math, and I'll see you guys next time. Bye.